Okay, so for this video, I will be discussing about how to set up a SolidWorks motion analysis. So I will be using an introduction to solid modeling using SolidWorks 2013, and I will be using this for the SolidWorks motion tutorial. So first, we will have three topics in this PDF, which is rotation of a wheel, four-bar linkage, and roller on a ramp. On our first discussion, we will discuss about the rotation of a wheel. Okay? So for the rotation of the wheel, we need to model wheel 1, wheel 2, and the base. So all dimensions are inches. So these are the dimensions needed. So you need to model this wheel 1, wheel 2, and base in order to proceed with the SolidWorks motion analysis tutorial. Okay, after doing that, we will be able to simulate the motion analysis. So to begin, we need to analyze a simple model of a wheel. So first is we open the file. So I have this wheel 1. This is wheel 1. You can see. So I will be opening my SolidWorks uh, software, which is 2021. So let's wait for this. Okay, so now my model wheel 1 is already open, and we will also open wheel 2. So this is the model for wheel 2. Okay. So I put the already the material alloy steel, and also we will open the base. So this is the base. All right. So all of which are being given a material of alloy steel as stated in the PDF. Okay. So first is this motion analysis will confirm that we are dealing with the Newton's second law of motion, which is summation of forces is equal to mass times the acceleration, wherein since this is a rotating body, we will get the summation of moments about an axis through the body's center of mass, where I is the mass moment of inertia and alpha is the angular acceleration of the mass moment of inertia about an axis, wherein I is equal to mr squared dv, where r is the radial distance from the axis. For simple shapes, is the relatively easy to calculate. I is basic shape as are tabulated in many reference books. So first is we will open part wheel 1. So for this one, we will be able to see that the mass is 15.29, while the moment of inertia about the z-axis is 105.36 pound per square inch, wherein this is labeled as LZZ. So let us check the model. So open wheel 1. Okay, so first we will go to the evaluate and mass properties. Okay, so as discussed, so moment of inertia as indicated LZZ is 105.36 pound square inches. So why Z? Because we are in the Z axis. Okay? So this determines that we have the same value, right? Then we'll go to the mass. It should be about 15.29 pounds. Okay, so the mass is about 15.29 pounds. And PZ is also 105.36. So this is the principal axis of inertia and principal moments of inertia. Okay, so they have the same value, 105.36 pounds square inches. Okay, so we have verified that we have the same model. So now we will compare it to wheel 2. So let's open wheel 2. Notice you have more mass outside of the wheel than concentrated inside as compared to wheel 1. So what does it mean? Okay, so note that the mass is about of 15.45 is almost the same as of wheel 1. So let's confirm what is the mass of this one. So this is about 15.45 pounds. So it's just about heavier than by about 6.16 pounds as compared to wheel 1. Okay? But as you will notice, the moment of inertia is 146.54 pounds square inch. This is about 40% greater than of wheel 1. So why is that so? So this is the value 146.54. Why is that so? Because based on our theory that the contribution of each particle of mass depends on the distance from the axis squared, meaning more mass on the outer rim means you have increased moment of inertia greatly. Okay, so now we will start the motion analysis. So first is we have to make an assembly. So since the base would be the fix, so we will first make that assembly part as the base. So close it. Then let's open the base. Okay, so let's make an assembly. So file make assembly from part. Okay, let's this base. Okay, then I will insert component wheel 1. Okay, so this should not be made. So let's make it float. Right. So let's mate it. This one is concentric to the base, while the face is coincident. Okay. So after that, you will be able to rotate the wheel one. Alright. So save uh, wheel motion analysis. Okay. So once we have the setup, first, the next thing we will do is click the Motion Study 1 tab near the lower left corner, which opens the Motion Manager across. So this one. So make sure before you click that one, you have the ideal view. Okay. Click the Motion Study 1. So now we are in the Motion Study toolbar. Okay. So notice that we have two types of study already available, animation and the basic motion. Animation is just you will able to rotate it. Only the motor is open, while the basic motion it will include springs and other such as gravity. Okay, so once we have this one, we'll be able to see animation, the basic motion, and of course the motion analysis, in which we want this be open because we will allow calculation of velocities, acceleration, forces for components during the motion analysis. So from the main menu, choose tools, add-ins in the list, and beside SolidWorks motion to activate it. So let's go to the tools. So let's look for SolidWorks motion analysis. So toolbars. Okay. Okay. So now check the active add-ins. Make this SolidWorks motion active. Click OK. So after clicking OK, we will see that we already activated the motion analysis. So that is on the add-ins. Okay, so once we already selected the motion analysis, first is we will select the force tool. So to apply a torque to the wheel. So we will set the torque to have a constant value of 5 inch-pound and we will apply it for a duration of 2 seconds. So in the force property manager, select torque since we are rotating this one and click the front face of the wheel. Okay, so now let's do it. So look for the force, select torque, so select the face. So make sure that the arrow is pointing counterclockwise. So input the torque. So as been stated, this is 5 pound force inch. So the Z axis will be the torque's direction below the face selection box because we are along the Z axis. Okay, so once we have the setup, check this one, then forget to select motion analysis. All right, so once we have that, let's go to the motion study properties. So click and drag the diamond shape, and from the default 5 seconds, let's go to the desired 2 seconds. So this is the diamond that the module is talking about. So adjust this time. So if we want to make it a bit detailed, so we could adjust this one. Zoom in, zoom out. Okay. Once we set up the time, let's go to the icon calculate. But first is we have to set the frames per second to 100. Okay, so let's go to the motion study properties. So we will have a more detailed frames per seconds by adding it from 25 to 100. Okay, then select calculate. So from the calculate button, this is the calculate. So we'll be able to run the simulation for the wheel. Alright, so notice that if I will play it from start, it is now rotating. Actually, you could make it playback in normal, playback loop. When you say playback loop, playback reciprocate. So it's moving clockwise, counterclockwise. Alright, so playback normal. Actually, you could also make this more slower, as you can see, by selecting the playback speed. Okay, alright. So next will be, so since this is motion analysis, we should have the value for our motion analysis. So as noted earlier, SolidWorks Motion will provide quantitative analysis results in addition to the qualitative animation of the motion models. So in the result plot, we will select for the angular acceleration Z component and we will select the front face. So we will be able to get the value of 1050 as the angular acceleration. So 1050 degrees per second squared. Okay, so let's go to the result plot. Select category, displacement, angular acceleration, z component because we are in the z axis. Select the phase and create a plot. So as you can see, we have the same plot as expected. So if we will play this one, you can see the red line from 0 to 2 seconds. It's constant about 1050 degrees per second squared. Alright, so we'll just check if SolidWorks Motion is giving us the right uh, computation if we will go by hand. So we discuss about the mass moment of inertia is about 105.36. So since the pound is actually a unit of force, not mass, we need to convert it by weight by dividing the gravitational acceleration, which is weight is equal to mass times gravity. Since we are using inches in our units of length, we will use 386.1 inches per second squared. So by applying the formula, we will be able to get 0.2729 pound inch per second squared, wherein we will be able to get the angular acceleration of about 18.323 radians per second squared, which in this is the torque over the 0.2729 pound per inch squared that we have computed. So with this, we will be able to get by converting it to radians to degree. So we will be able to get 1050 degree per second squared. So what does it mean? So based on hand computation, our value is just the same. So it means that SolidWorks is giving us the correct answer. So now let's move on to the exercise. So we will get the as expected, since the acceleration is constant, the velocity increases linearly. The velocity at the end of 2 seconds is about 2100 degrees per second squared. So we will be able to verify it by 1050 times 2, which is the is equal to 2100 degree per second. Okay, so often the angular velocity is expressed in revolutions per minute. So we will convert it to from 2100 degrees per second, and we will convert it to revolutions per minute of about 350 revolutions. So let's model this one. So I will be going to the result plot, displacement, angular velocity, z component, that's the phase, and I'm showing to you the value of 2100 per second. Okay, so let's do some more exercise. So let's move the plots out of the way but do not close them. Click and drag at the key. Tap from 2 seconds to 4 seconds. So the simulation will now last for 4 seconds. So let's move it to the key 4 seconds. But also we could do this. Edit key point time 4 seconds. Okay. A new key will be placed at that location. So the torque will now be applied for 2 seconds, but the simulation will continue for the 4 seconds. Okay, so per module, we need to stop the torque at 2 seconds. So we'll go back here from 0. The torque will be applied at 2 seconds and we'll rotate till 4 seconds. So let's click calculate. So should be expecting a value of Okay, so what did you see? The angular velocity is gradually increases from 0 to 2100 and stay constant after 2 seconds, while the angular acceleration is constant at 1050, then drops to 0 after 2 seconds. So let's see if we have the same graph. Okay, so this means that we are applying the simulation good enough. Okay, so the wheel will continue to spin at a constant velocity without any torque applied. So we're doing a good job. So then right click at the key added to the torque at 2 seconds and delete it. So let's delete it. Delete. Okay. So move the time back to 0. Move the time back to 0. Then right click on the torque and select edit feature and select segment. So right click, edit feature. From the constant, we will go to segments. Okay, so this one is the tab for the segment. So we have to input 0 to 2, 5 pound force inch. So this is click to add row 0 to 2, 5. Click add row 2 to 4, 5, 4 to 6, 0. Okay, so we will be able to get this graph. So is it showing the same graph that we have? So it should be 0, 5, 5, 0. So 0, 5, 5, 0. Okay, so we have the graph already. I think we have the same graph. Click OK. Then calculate the simulation. So we should be able to get this kind of graph. So note that the angular acceleration. Okay, so check this one, then calculate. Okay, so what happened to the model? So it does not show what we are expecting. So 3149 to 1050. So I need to go back to the PDF so can see that I may be I may lose some details for this one. Right click at to move the key finding. Okay, duration to the simulation to 6 seconds. So sorry for that. So I should be applying 6 seconds. Sorry for that. So that's why the graph is different from the PDF. So I missed that. Alright. So you can see that the angular acceleration is smooth about 1050 from time 1.8 up to 4.2. So let's see the data if we have this. And the angular velocity peak from 4,202 degrees per second. So we have a minimal discrepancy of 3 points, but we have the same angular acceleration. So I get 4,199 as compared to the 4,202. So I think it's just a minor difference. So Now let's see the effect of replacing wheel 1 component with wheel 2, which has the higher mass. So we will be applying replace command. So there should be automatic replacement of wheel 1 to wheel 2. So let's click save first, right? So let's go to the assembly model, then file. So let's look for the replace these components. So replace wheel 1 with this one, then check. Then there will be a warning, then face of wheel 2 goes. Okay, so if the replacement is good, and voila. So you will be able to rotate the wheel with no issue. It will copy the mates that you did for the wheel 1 model. Okay, let's go back to the motion study and calculate. As simple as that. But what will happen? It will not rotate because you need to update where is the torque. Okay, so the phase is missing. Okay, so calculate. Now you have your model. So this is not straightforward, so that's why we are simulating it. Okay, so as you can notice, the angular acceleration drops to 755 and the angular velocity drops to 3019 degree per second. So this is the same results that we have in our PDF. So we are able to get about angular velocity of 3019 and the angular acceleration drops to 755. So let's do the hand computation. So based on this ratio and proportion, since the maximum angular acceleration is about 755 degrees per second, which is significantly less that of the simulation, the earlier wheel, which is wheel 1, by applying this, so the angular acceleration will be I1 over I2 times the angular acceleration of wheel 1, which is 105.36 over 146.54 times the angular acceleration of about 1050 degrees per second squared, which is 755 degree per second squared. So our simulation don't lie. So we are able to get 755. Save all, and that's it for our simulation on wheel 1. Thank you for this one.